In the previous screencast, we studied work. In this one, we're going to look at flow and circulation. The idea is essentially that flow and circulation are basically the same as work. The only difference is the interpretation. Work in the last unit we looked at was a force times a displacement. And we added up the force times the little bits of displacement to get the entire work done. Well, in this case, you can think of this as really the force dotted with the tangent vector is really just how much of the force is in the direction of the tangent vector, and then multiply that by ds and add it up. Well, flow is, rather than thinking of it as a Newton or some force that's a Newton, instead we're going to think of the F as now some velocity. So we've got something moving. We've got a meter per second. Air is flowing, water is moving, and it's of meters per second. And I want to know how much of that is moving in the direction of a curve. So I'll dot it with t to find that amount, and then I want to add that up along the entire curve. This quantity, which is essentially the same as work, is just where do you put the parentheses. Flow is, you can think of it as to basically work. But it's a velocity rather than some kind of Newton. Well, circulation is equal to flow on a closed curve. This quantity is studied by people who study airflow. If you're going to make airplanes, you're studying the flow of vector fields over wings. And how in the world do you get it? Well, what in the world does closed curve mean? The idea, if you've got a curve and it starts somewhere and goes around and eventually ends at the same point, a closed curve is starts and ends at the same point. Now, in the last unit, we took this integral and we also wrote it in the form c m dx plus n dy. Well, this is really the same thing as flow. It's the same thing. If it happens to be on a closed curve, then we add a circle to the integral. And this just tells us that it's actually going along a curve. And when we start talking about circulation, we're always going to be looking at the counterclockwise circulation. So sometimes people on their integral will put a little arrow to denote they're going in the counterclockwise direction. If you see that symbol, it just means you're doing an integral along a closed curve. Let's take an example. Suppose our vector field is x plus y, and then xy. Let's find the circulation along a curve, and here is our curve. We're going to take a triangle. We're going to go over 3 units in the x, up 2 in the y, and we'll have the other point be the origin. And we're going to go along this curve. That's 3 curves, actually. We've got a C1, a C2, and a C3. Let's find the circulation of F along counterclockwise along C, which is the union of these 3 curves. So if I start here and move all the way around in a circle and come back, what is the circulation, or how much work is done is another way you could look at it. To answer that question, I actually have to parameterize all 3 curves. Remember, the idea is I can do head minus tail times t plus the tail. So we'll start with the first curve, R1. I need to parameterize it. To parameterize it, well, I need the head minus the tail. So I've got the 3 minus 0. So 3, in the y direction we're not going anywhere. We'll times that by t, and I need to add the tail. The tail is 0, 0. R2, let's parameterize that. So curve 2, head minus tail. The x direction goes back 3. The y direction goes up 2. Now you could just think, oh wait, I'm going left 3, up 2. Times t plus, and the place I started at was 3, 0. I also need a third parameterization, so we'll write R3 of t. And that one, I'm going none in the x, I'm going down 2 in the y. Got to times that by t, and let's add where we started, which was at 0, 2. Alright, so now that we've got each of the parameterizations, remember to compute this, really, we're just computing f dot dr. So I need to know what's dr, or what's r1 prime. And in this case, it's just 3, 0. it's really just that vector in each case. So r2 prime is negative 3, 2, and r3 prime is 0, negative 2. Now, it's going to help us later if we'll just actually get rid of the plus sign. I'm going to rewrite r1 as 3t, comma 0. r2 is, we've got a minus 3t plus 3, and then a 2t. And r3 is 0, and then minus 2t plus 2. In every single one of these, our bounds are always t is going from 0 to 1. We're now ready to set up our integrals. So, the first integral, I need to take f. Let's actually put x, y in for f before we integrate. So what is f? Well, it's x plus y, which means it's 3t plus 0, comma, and then multiplying 0. Let's find r2. Or not r2, let's find f when we're on r2. F is, let's take that one plus that one, so minus 3t plus 3 plus 2t. And then I got to multiply them, minus 3t plus 3 times 2t. That one's bigger. And then I need my one on the third one, and this one is just add them, minus 2t plus 2, and then multiply them. We are now ready. We've got our f vector on each of the curves, so we can now set them up. On the first curve, we have to dot our prime and f. So if we dot these two, we get 3 and 3t plus 0. So that's our first integral. That takes care of the work on this one. Now our second one, we integrate from 0 to 1, and I've got to dot these again. So here I get a negative 3, and I get a minus 3t plus 3 plus 2t, and then plus 2 times negative 3t plus 3 times 2t dt. And then the last integral, I'm going to go from 0 to 1, and I dot them. Notice that's 0 plus 0. So that integral is 0. We have a picture to represent this one, and the idea is here is the vector field, and the answers end up being on this curve there's no work done. On this curve it's minus 11 halves, and on the bottom curve it's 9 halves. These integrals simplify to these numbers. That completes the screen.